Cables are used in buildings, bridges, transmission towers, and long span structures. The key feature of cables is that they resist tension only. They don't take any compression, shear, or bending moments. In this tutorial, I will cover 3 examples, and after watching them, you will have some kind of expertise in solving cable structures. Hey friends, if you're new here, I am Dr. Jawed Qureshi, a senior lecturer at University of East London. On this channel, we explore civil engineering and human skills to help us lead more productive, happy, and examined life. Before I go through examples, I would like to cover the basics of cables and where they are used. Cables are used in suspension structures where structural elements are suspended from cables, and cables are attached to some kind of firm support that can be a tower or another structure. You would have seen cables in suspension bridges. And what are suspension bridges? In suspension structures, the main cables, they are attached with the towers, and there are secondary vertical cables that you see over here. They are attached with the main cables, and a bridge deck is supported on these cables. The function of towers is that they support main cables, and again main cables are attached to some kind of anchorage on the other side. Now, what is the load path? Load is transferred to main cables, and from main cables to towers, and from towers to some anchorage point. This is the diagram which tells us the main function of these cables. Here they are attached with the towers. The vertical cables are termed as hangers. They are equally spaced, and these cables, they support the bridge deck. And here we have some stiffening trusses as well. And finally, the main cable is attached with some kind of anchor points at the ends. This type of bridge is termed as suspension bridge. The main examples of suspension bridges are Brooklyn Bridge in USA, which is the top right bridge, and Golden Gate Bridge, the bottom right bridge. Both bridges are in USA. Cables are also used in cable-stayed bridge. The key difference here is that the deck is supported by cables which are directly connected to towers. The load distribution is different, and the pattern is like a fan. The examples of cable-stayed bridges include Millau Viaduct Bridge in France and Øresund Bridge that runs between Denmark and Sweden. This is a picture showing Millau Viaduct Bridge, and on right side you can see Øresund Bridge. This is a kind of hybrid bridge. At the end of the bridge over here, there's a tunnel, so it becomes a tunnel which goes under the sea. This diagram shows cable-stayed bridges. We have main support towers, and they are compression members, and we have cables that take tension. Load of bridge deck is supported by cables, and then it goes to towers. Type of cable: there are mainly 2 types of cables: parallel wire cables, a series of high strength steel cables, and secondly we have strand cables where a series of wires are wound in helical fashion. These are 2 types of cables. Again, here you can see 3 types of cable. First one is a strand, the second one is Z-lock cable, and third one is a wire rope cable. I will be solving 3 examples here, and there will be timestamps down in description, so feel free to switch between the examples. The first example will be on finding tension forces, reactions for a cable structure where the supports are even at the same level. The second example will be cable structure where you will have supports at different levels. The third example is taken from IStructE certificate in structural behavior. It is a very simple question, and I will solve that question here as well. This is part of my video series on IStructE certificate in structural behavior. If you are preparing for that exam, or if you want to improve your general understanding of basic structural analysis using simple formula, this tutorial is for you. I will now move to the first example where both supports they are at the same level. So here cable is subjected to concentrated load. A and E, they have pin supports, and the sag C is known as 1.8 meters. So we have this sagging known. Ignoring the self weight, we have to determine the values of support reactions at A and E and the values of dip or sagging at B and D. It means that we have to determine HB and we have to determine HD as well. And 3 concentrated point loads are applied: 15 kilonewton, 20 kilonewton and 20 kilonewton. And thirdly, we have to determine values of tension forces for individual segments of the cable. So it means that for each individual segment, A to B, B to C, C to D and D to E, we have to determine tension. Here is the solution. So first we have to determine the support reactions at A and E. For that, we have to take summation of moments at E is equal to 0. In other words, we can say rotational equilibrium of cable about E is 0. Clockwise moments are considered as positive. Starting with VA, the distance between VA and E is 10 meters. So 10 times VA, it is creating clockwise moment. That's the reason it's positive. And then we have this 15, the distance between 15 and point E is 7, and it is creating, because it's downward, it's creating anti-clockwise moment. That's the reason it is negative here. And then we have 20 times the distance between C and E is 5, so that's why we multiplied with 5. And finally we have another 20 kilonewton and its distance from E is 3. It is anti-clockwise as well. If we simplify it, we get value of vertical reaction at A as 26.5 kilonewton, and it is positive. Positive is upwards. Then we consider vertical equilibrium. So summation of vertical forces Fz is equal to 0 and positive forces are upwards. So we have VA, we have VE, which are upward forces, and at BCD we have vertical forces and these are downwards. So that's why these are negative. So if we sum it up and if we put value of VA into this equation, we get value of VE, vertical reaction, that is pointing upwards. Next thing, we have to consider the left part of the cable and consider rotational equilibrium at C. So we are saying that moment at C is equal to 0. And the reason we have done it because we have this HC known. So 5A, 5 times VA, it means that this vertical reaction has got a lever arm between A and C as 5. So that's the reason we have 5 here. And HA is pointing leftwards. The distance between H and this point C is 1.8. So that's the reason we have 1.8 here. And we have this 15 kilonewton, which is 2 meters away from C. So that's the reason we have 15 times 2, and it is creating anti-clockwise moment. If we simplify it, the value of H comes out to be 56.94 kilonewton, and it is pointing towards left. It means that the assumed direction is fine. Let us now determine values of sags at B and D. This is B and this is D. Select the left part of the cable and considering moment equilibrium. So now we are working out summation of moment at B is equal to 0. We are just considering the left part, and the reason we are able to do it because the cable cannot take any moment. So that's the reason at any part the moment is going to be 0. So VA has a lever arm of 3, so that's why it's 3 VA, and H has lever arm of HB and it is anti-clockwise moment, and from here we can determine value of HB, that is sag or dip at B, as 1.396, And then we move to the right part of the cable and considering the moment equilibrium at D. So now we are concerned with the right part. And from here, we can say H times HD. So the distance between H and D vertically is HD. This vertical reaction is creating anti-clockwise moment with respect to D, and the distance is 3 meters. And if we simplify it, we will get value of HD as 1.5 meters. Once we have determined the sag at H and D and reactions at VA and VE, then we will determine value of tension forces for individual segments of the cable. First, I have to determine this angle, which is theta AB. This will be equal to vertical force divided by horizontal force. So tangent is equal to opposite divided by adjacent. So opposite force is vertical, which is VA, and adjacent is H. So tangent inverse VA over H, I will get value as 24.96 degrees, or I can say roughly 25 degrees as well. Then we will consider horizontal equilibrium at point A, the summation of all horizontal forces. So I'm considering the segment AB only here. So minus H, and then TAB is the tension force in this segment. When I want a tension force, the horizontal component of this inclined force will be T cos theta. So it is TAB cos theta, and it is pointing rightwards because there is a tension over here. So arrows are pointing away from the joint. And from here, I already have theta AB, which is about 25. So if we put the values, you get TAB as 62.8 kilonewton. And in the same way, vertical equilibrium at point A, vertical forces are 0. So VA is upwards, and the vertical component here will be downwards. So TAB sine theta AB, if we put the values, you can see that all vertical forces are 0. Now this is telling us a very important thing, that is that the cables, they do not take any shear force. So there is no shear force at all, and when there is no shear force, there is no bending as well. Let me move to the another segment, B and C. So this is the segment, this angle is theta BC. First we have to determine theta BC. So it will be tangent inverse of vertical over horizontal dimension. Vertical dimension is this one, which I'm looking for. HB is equal to 1.396. So to find out this dimension, I have to subtract 1.396 from 1.8. So that's what I've done over here. And from here, I can find out the angle. And in the same way, considering the horizontal equilibrium for this segment at B, I have TAB. So earlier I had these forces. So here the arrows are pointing away from the joint. So here I will have the horizontal component TBC, and this is TAB. TAB is pointing leftward, so that's why it's negative. TBC is pointing rightward, so that's why it is positive. So from here, if you put values of angles, TAB we determined a little earlier. From here, we can work out TBC, which is 58 kilonewton. And then again, we check the vertical equilibrium at point B. It should be 0. So when we put all these values, it becomes 0. The next is this segment between D and E. So tangent DE at point E, I have this angle DE, where I find out using the same logic this equation, and then considering horizontal equilibrium, I find out TDE, and from here the vertical equilibrium is 0. And then I move to joint D, and again in the same way I will find out the angle, and then summation of horizontal forces. I find out TCD, and then the vertical forces are 0 using the same logic. And finally, we check equilibrium at point C, both horizontal and vertical. So at point C, we have horizontal equilibrium as 0 and we have vertical equilibrium as 0. This means that whatever calculations we have done, these calculations are fine. Now I move to another example where we have concentrated loads but with uneven supports. So here the level of A and E, it is not the same. The sag at B is given, which is 3 meters. So only sagging at this point is given, which is 3 meters. So we have to determine the values of tension forces for individual segments and the value of support reactions at A and B and values of sag at C and D, and we have to determine the total length of the cable. First thing first, we want to determine theta AB. So it is this angle over here. It is equal to vertical over horizontal. So if you have a look at this dimension, the vertical is 3, the horizontal is 2.5. From here we determine the angle, and then rotational equilibrium at point E, summation of moments at E. TAB sin theta is a vertical force, and that is upward force, and it is 7.5 meters away from point E. And then we have 1.5 times TAB cos theta, because the distance between this point and this point is 1.5, which is here, and then 30 into 7.5, this is the vertical load over here, and then 60 into 5, it is this vertical load, and 30 into 2.5, it is this vertical load. From here we can find out TAB as 89.26. so tension in this member is known now, and then we work out the horizontal equilibrium at point B, which is this point. So minus TAB, because it's going towards left, plus TBC cos theta BC. This is first equation, and then we have summation of vertical forces equal to 0. Vertical forces at this point will be TAB sin theta AB, and the TBC sin theta BC is downwards, and we have a downward force as well. And we rearrange these two equations, and from here there will be simultaneous equations, and from here we work out the value of tension. Once we have got these values, then we will work out theta BC, which is the vertical force, which is TBC sin theta BC, 38, divided by a horizontal force, which is here. From here we work out the angle. And similarly we move to joint C and apply the horizontal equilibrium and vertical equilibrium, rearrange the equations, apply the same process, we work out TCD, and we work out the angle as well. And using the same logic at point D, we establish, it's repetitive, we establish TDE and we establish theta DE. And finally the values of support reactions at A and B. So we consider horizontal equilibrium at A, summation of all horizontal forces equal to A. Now we have got values of theta AB, and from here we work out HA as 57.15, and we consider vertical equilibrium from here at point A. From here we work out value of vertical reaction as 68.57, and finally at point E the horizontal equilibrium leads to 57.15 and vertical equilibrium leads to 51.44. Note one thing here, that the horizontal reaction here at A and horizontal reaction at E, both horizontal reactions are same. This is really very important. In cables, horizontal reaction will be same at supports, no matter if we have even or uneven supports. This is absolutely crucial. Note it down. This is a really very important point. And finally we have to determine values of sag at C and D relevant to support E. So here we sum up all the vertical components. So HC in total is equal to this value, which is 1.5, plus this component. If I call this component as X, and this is theta BC, tangent of theta BC will be equal to vertical over horizontal. Horizontal is 2.5, which means x will be equal to 2.5 tangent of theta BC. That's where I've got this value, and from here you can work out the total value of HC. Using the same logic, we work out HD as well as 2.25, and then using trigonometry we work out the total length of the cable as well. And how did we come up with this one? If we have a triangle, so this is the length of the cable, this is angle, for example theta AB, and this is the horizontal reaction, horizontal value, which means that 2.5. So if I say cos theta AB will be equal to adjacent, which is 2.5, divided by hypotenuse, which is L. And if you rearrange this, L will be equal to 2.5 divided by cos theta AB. And similarly cos theta BC, CD and DE. From here we work out the total length of the cable. And then I will move to IStructE question. Here we have to determine the horizontal reaction at each end of the cable and what is the maximum dip D. And there are 4 options to choose from. I suggest that you try this question first by going to this URL or scan this barcode before watching the solution. So pause this video now and try this question first. First, we need to determine the vertical reactions. If I call this as VA, this is VB, this point is A, this is B. Summation of vertical forces is equal to 0. VA and VB is equal to total load, which is 20 plus 40, 60 kilonewton. Treat this as a beam and use this logic, load time off span divided by full span. So if this is a simply supported structure, if you have this point load applied and this is the length, reaction A, for example, here is equal to load times off span. I call this as B, I call this as A. Load times off span divided by full span. So here for 20, off span is the one which is away from here. So 4 plus 4, 8, divided by full span is 10. Again for 40, off span is 4 meters, divided by full span is 10. From here I can directly work out value of reaction. If I put this value back in here, I get value of VB as 28, or again I apply the same logic to reaction B, starting with 20, load times off span is now 2 divided by full span. For 40, off span now is addition of 2 and 4, 6 divided by full span is 10, and from here I get value of reaction as 28 kilonewton. Once I've got reactions, then I will draw a free body diagram at point C. So we have 20 kilonewton. I call this point as C and I call this point as D. So free body cut at C, it will give me this value. I have reaction VA as 32 and I have the dip as 2 meters. HA, the summation of moments at C equal to 0. Because this is a cable, at any point the moment is going to be 0. So 32 times 2, this vertical reaction is creating a moment that is clockwise moment, so that's why it is positive. And HA is this one, it is creating anti-clockwise moment, so that's the reason I put it on the other side of equation. From here I get value of HA as 32 kilonewton. Because this is a cable structure, the reactions are going to be same, so that's why HB will be equal to 32 kilonewton as well. And you saw in earlier example that reactions were same. Now I take a free body cut at D, which is this point. From here you label all the forces. The horizontal reaction at B is 32, vertical is 28, and we have a load of 40 kilonewton. Summation of moments at D equal to 0. VB times 4, it is creating anti-clockwise moment, so that's why it is negative, and then HB times D. Now we have got value of HB 32, VB 28. So from here I can work out value of D, which is dip at the end, and it comes out to be 3.5. So dip is 3.5 and the horizontal reaction is 32. So our correct answer is option B, where we have horizontal reaction as 32 and dip as 3.5 meters. Now tell me, did you get this right? If you didn't, then there's no need to worry. Always watch back this tutorial. If you want to see other similar videos, go to this URL or scan this barcode to watch similar tutorials. The link will be down in description as well. If you want to solve these questions as you go on and have a look at the lecture slides, go to this URL and scan this barcode. You'll be able to download all the lecture slides.